Okay, hello. So in this video, I want to go over the next bit, which is to actually do a full hypothesis test, because before all we've done is done sort of effectively bits of it. Now, in many ways, you've done all the conceptual heavy lifting, so there's no new concepts here. This is just about putting it all together. Okay, so let's begin here. So let's see if I can get this to work. Right, so back to our favorite example about tossing a coin 8 times and it coming up heads 6 times. And so John claims his coin is biased towards head. And so with a significance level of 5%, test this claim. So this is the way you would see it most of the time written in the exam. So how are we going to do this? So the first thing we need to do is to define my test statistic. So we've done this already before. So my test statistic here, in this case, is going to be the number of heads. And it's true, in this case, that x has a binomial distribution, right? And I'm tossing the coin 8 times, and my parameter, the thing I don't really know, is p. Okay, so I'm testing whether or not the coin is biased, so p would be the probability of getting heads. Okay, this is crucial. Write the null and the alternative hypothesis. It's crucial for 2 reasons. 1, because it's just good practice, and 2, because there are actually marks for it, sometimes up to 2 marks for it. And so it is very, 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 very stupid to not do this, and it is really straightforward. So H0 is P is a half, I know that. Null hypothesis is saying nothing particularly interesting is going on, nothing's changed, so it's just saying probability is a half. H1, the alternative hypothesis, well then, see, I'm checking whether it's biased towards heads, so I'm going to say that probability is greater than a half. So this is a one-tailed test. So that's all I'm doing in this video, one-tailed. Two-tailed is fairly similar, but I'll just do one-tailed in this particular situation. So that's step 2. Step 3 is to determine the p-value. Okay, so the p-value, if you remember, is the probability of getting the test statistic you observe, which in this case is 6 times, right? You'll see. Or something more extreme. Remember, because the reason we do that is because it might just be it's unlikely because there's lots of different possible outcomes. So you need to account for things that, so the results you get, or things that would constitute even stronger evidence. So you need to ask then, so say, under H0, so I am assuming the null hypothesis because I'm assuming that probability is a half, because otherwise I wouldn't know how to work out the probability with an unknown p. So under that null hypothesis, the probability of x being bigger than or equal to, 6? And why is it bigger than or equal to? Because what would constitute more extreme evidence of the coin being biased is if I had even more heads. So I can use a calculator for this, or I just use a table. So here I want probability of x bigger than or equal to 6. So that's 1 minus probability of x less than or equal to 5. Remember, so the opposite of being bigger than or equal to 6 is less than or equal to 5. That's 1 minus, just reading off here, 0.8. Oh, why does it do that? 1 minus 0.8555. Sorry about that. So this should be 0.1445. Okay, so we've worked that out. But in this case, I am not done. And it is really important that I realize I'm not done, because I need to write a conclusion. And usually the conclusion carries 2 marks because it's a 2-part conclusion. One of it is, do I reject H0, the null hypothesis or not? And remember, the language here is, do I reject the null hypothesis or do I fail to reject the null hypothesis? Okay, there is no accepting the null hypothesis, there is no accepting the alternative hypothesis or rejecting the alternative hypothesis. It's only, do I reject ho or not? And the second bit, which people always seem to forget, is that you need to put it in context of the original problem. In this case, is the coin biased towards heads? So the significance level is 5%. This probability is higher, so we're saying this is still a reasonably likely occurrence. So I fail to reject, so insufficient evidence, I know you're right, to reject H0, null hypothesis. So I'd say this coin is not biased. So again, this is my, do I reject it? So I make a comparison at the significance level and say the coin is not biased. That's my context. Right. There's another way of doing this, which is to use a critical region. And your mark scheme would give you both ways of doing this. So you start the same way, you define your test statistic and your parameter, you'd write your hypotheses. The alternative, one thing I will say actually, just, it is really important to write the p here for the hypotheses, I have seen people write things like H0 equals 0.5, things like that. That's bad. Okay, do not do that. Okay, that's just wrong. Right, you need to write a P, in this case with probability. So, critical region, which if you've just been doing, what's the first one to go over 95%? That's this one. So you take the one above. So the critical region is, you would need to write, if you remember, this statement here. Critical region is x bigger than or equal to 7. And then the question is the test statistic you measure in the critical region, in this case it's not. So 6 is not in the critical region, so do not reject H0, or perhaps more correctly, you say fail to reject H0. And again, conclusion in context. Right, so here's another example. This one's from the textbook. So treatment for a disease has this probability of success, and you want to check whether a new drug works. I mean, testing on 20 patients is silly. You need to test on loads more, obviously. But the doctor claims the drug represents an improvement. So this improvement thing, it tells you this is a one-tail test because it's telling you that the probability of success is increasing. Okay, and you're told the significance level as well. So again, key things here is the significance level, this probability, which is going to be your null hypothesis, and this 11, which is your test statistic, and 20, which is the number of things. So what's your test statistic? It's the number of patients where it's successful, P is the probability of success, and this is my distribution. What's my null and alternative hypotheses? Well, null hypothesis, nothing's changed, so H0 is 2/5, and the alternative hypothesis that it's improved. Okay, so 2/5, 0.4, often write as decimal. So, what am I actually trying to find? I'm trying to find the probability. Now, x being something with 11. So the question is it bigger than or equal to or less than or equal to? So what would represent a more stronger evidence against the null hypothesis? The null hypothesis being that this is probability of success, right? So this might not be necessarily obvious, but you think about it. So if you have 20 patients and if you expect 2/5 of them to get well on the null hypothesis, that's going to be, well, 2/5 of 20 is 8, okay? So this is above 8, so what would, this 11 is above 8, so what would represent more extreme evidence? Well, even more patients getting better, so I want probability of x being bigger than or equal to 11, okay? This is perhaps the only bit here that's a little bit, that might need a little bit more thought each time you do it. Okay, so then what do? I work out this probability. So again, you say, assume H0 is true or under H0, this is my distribution, so you work this out. Okay, and then you say you compare. Now in this case, 0.1275 is bigger probability than 5%. So we're saying if the drug has a success rate of 2/5, the probability that you get 11 or more recoveries is this, so that's reasonably likely comparatively to happen by chance. So not enough evidence to reject the whole. And so your conclusion in context, again, really important, is that the new drug is no better than the old one. Okay, so there's a couple of exam questions I want to do now. So you can either pause it and have a go at yourself, or you can just watch me do this. So someone grows tomatoes, probability of 0.3 of ripe tomato. So you're told key information here is this 0.3, that's my null hypothesis. The 4 centimeters here is neither here nor there, because it's just, well, that's my success is whether a tomato has a diameter greater than 4 centimeters. So random sample 40, 18, that's my test statistic. And she's claiming that it's increased, so it's a one-tail test, and it's my 5% significance level. So I'm going to say x equals number of tomatoes bigger than 4 centimeters. I don't know why it does that, sorry. So, and then x binomial distribution, 40 tomatoes with probability p. Okay, so what am I testing? H0 is that p equals 0.3, because that's what I had here, what I'm told, and because she's saying it's increased, so H1 is that probability is bigger than that. So what do I do now? Well, I want to work out the probability, so under H0, comma, probability of x. Now, 30% of 0.3 times 40, so you expect about 12 of them. 18 is more, so something even more extreme would be x bigger than or equal to 18, right? So that's 1 minus the probability of x less than or equal to 17. So this you can do the table. Sometimes you'll get probabilities here you can't do the tables, in which case you do them with your calculator. So if you work this out, this is 0.0320 to 3 significant figures. I've done this with my calculator, so if you've done it with the table, you might get a slightly different thing. Okay, the key thing is this is less than 5%. So my conclusion is as 0.0320 less than 0.05, not enough. Oh, so, whoops, nope, wrong. That is not right. Because this is unlikely enough, we do reject the null hypothesis. Reject H0, or enough evidence to reject H0. So that's part 1. Therefore, so my conclusion is context. Just looking back up here at my question, claims the new fertilizer increased probability of a ripe tomato. The new fertilizer has increased the probability. Okay, so if we look at the mark scheme, you'll see there are 2 marks, and I kid you not, 2 marks for writing the hypotheses. It is they are the silliest marks to drop. Okay, then writing this out, so x representing this, then there's 2 ways of doing this. So you see there's the kind of split here. One way is to do what I've done, which is to work out the probability. The other one is to work out the critical region. Okay, either way would work. That would get you no evidence to reject. No, there is evidence to reject H0. This is a typo. And so 1 mark is for, again, to rejecting H0, and the other one, oops, which it seems actually that I would have got this wrong, increased probability to being greater, or indeed you could say instead her claim is true, which is probably easier. Okay, last one. So student taking multiple choice tests, have a quick go at that one. Okay, so if you've had a go at that one, again, you notice that the way this is asked is state your hypotheses clearly. So how does this work? You get 1 mark for the hypothesis, 1 mark for saying this. Now, if you say it like this, that's fine, under H0. You can also say it when you define your x equals and you say x is binomial 10p. You would probably get the mark the same way there. Notice it says bi, and that's just another way of doing it. And more conventionally, you just write a b. And one way you either work out the probability or you work out the critical region. But whichever way, you say either because the 4 questions is not in the critical region, or because the probability is bigger than 0.5, there's insufficient evidence to reject null hypothesis, 1 mark, so teacher's claim is supported. Okay. Right, so I think that should be enough for you to have a go at exercise 7c, but any questions, do just email me or Miss Anderson. Right, good, see you soon, bye.